Okay, so after last example, let's try some example. We already know the answer and we want to verify our method. Okay, so we're going to integrate 1 over 1 plus x squared. We know this antiderivative. It's a tangent inverse of x and plus c. Okay, so what is the graph of tangent inverse of x? The top horizontal asymptote is y equal to pi over 2. The bottom horizontal asymptote is y equal to negative pi over 2. And the tangent inverse looks like this. So we know that from this graph, we know the limit at positive infinity, tangent inverse of x is pi over 2, and limit at negative infinity, tangent inverse of x is negative pi over 2. Okay, so by all these informations, we can see that the integral of 1 over 1 plus x squared dx is from negative infinity to positive infinity is pi over 2 minus negative pi over 2 is equal to pi. All right, so this is what we can get from the antiderivative. Now let's apply our residue theorem to this stuff. Okay, so we define f of z as a 1 over 1 plus z squared. And it has two simple poles. What are those simple poles? Remember that z squared is equal to negative 1, then z is I, and z is negative I. So z1 is I, z2 is negative I. So you have I is here and negative I is here. And let's try to compute the residue of function f with respect to I. Remember, it's a limit z approaches I, z minus I, f of z, right? So it is the limit z minus I, z, f of z, you can write it as 1 over z minus I and z plus I. And cancel z minus I from top and bottom, you will get 1 over z plus I. And you can do substitution, you get 1 over 2i or negative I over 2. Alright, so the residue of f with respect to I is negative I over 2. Okay, so we like the previous example, we only use the residue of this at this point. We don't need the other point, so we're not going to compute the other point. Now we're going to do what? We're going to do a integral. All right, so we're going to say let r greater than 1 and let gamma be the closed path which is the boundary of the upper half of the disk of radius r with center 0. So it's a long sentence. So basically we just get the upper semicircle, and together with this piece, this is r, this is negative r. r is greater than 1, so this whole path will enclose this I. Then we can apply the residue theorem. The residue theorem tells us, okay, so this is a very simple path. So the winding number is always 1. I mean, it's counterclockwise orientation. We didn't mention the counterclockwise orientation. All right, I forgot to mention here, counterclockwise. Okay, then we can see what? We can see the integral of f along this gamma times 1 over 2 pi I is equal to the residue of f with respect to I. Just one simple pole. One simple pole, and the winding number is 1, so it's equal to the residue. All right, and this winding number, this integral, it has two pieces. One piece is along the x-axis, the other piece is along the semicircle. So it is also equal to, residue. What is the residue? Residue is negative I over 2. Negative I over 2. The other way, this is 1 over 2 pi I integral what? From negative r to positive r, 1 over 1 plus x squared dx. This is the integral along the horizontal segment on the x-axis, and plus 1 over 2 pi I along this semicircle. The z is r e I t. Z is r e I t, so it's integral from 0 to pi dz is r e I t times I dt. Okay, so the integral is r e I t times I and dt. Denominator is 1 plus r squared e 2it. Okay, so you have integral along the x-axis and integral along the semicircle. You have two parts. Okay, so let's continue. We're going to, like what we did for the last example, we're going to estimate this piece. We're going to estimate this piece. So we see that this r squared e 2it, 1 plus it, this ups value is going to be greater than or equal to r squared minus 1. Similarly, like the last one. So 1 over 1 plus r squared e 2it absolute value is going to be less than or equal to 1 over r squared minus 1. Remember, r is greater than 1. All right, so let's try to compute this absolute value, integral from 0 to pi r e 2I, it times I dt plus 1 over r squared e 2it modulus. Apply the property of an integral is the integral 0 to pi, from 0 to pi, the numerator I denominator 2it dt. And numerator is just r. Numerator does not apply the inequality. Numerator is r. But the thing is the denominator. Denominator, we apply the inequality. It's less than or equal to r squared minus 1 dt. So this is equal to pi r over r squared minus 1. It will converge to 0 as r approaches infinity. Right? As r approaches infinity, we have it converged to 0. Okay. All right. So we're going to let r approach infinity. Remember this part, this is negative I over 2. It is equal to the sum. So the limit r approach infinity, negative I over 2 is equal to 1 over 2 pi I integral from negative infinity to positive infinity. This is still the negative I over 2. 1 over 1 plus x squared dx, and this part with the limit this limit will be 0. Alright, so this term will disappear. So you only have this one. This one we multiply two sides by 2 pi I. You will get pi is equal to the integral from negative infinity to positive infinity, 1 over 1 plus x squared dx. So you see here, we recover our answer. Alright, so at least we use this example to verify that our method will give us the same answer on the same problem. Right? So this is a nice problem. And from these two examples, we can see that how can we apply the similar strategy to other integrals. The thing is that we need to make sure that, you see here, whenever you have a dz integral, blah, 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 you have a dz, you have a numerator, you have a denominator. You need to make sure that the degree of the denominator is greater than or equal to the degree of the numerator plus 2, at least plus 2. So the last example we discussed, we get z squared over 1 plus z to 4th power. The difference of degrees is 2. In this example we discussed is 1 over 1 plus z squared. The difference is also 2. Why we require the difference of degrees is at least 2? It's because when you do the differential dz along this semicircle, you will create a radius r, and denominator you have a degree 2. So still with the help of this r, the degree of the denominator is still greater than or equal to the degree of the numerator. Here's a greater than 2, but with this r it becomes greater than 1. Right? The numerator has one more radius, one more factor of the radius. And when it is the degree of the denominator is greater than the degree of the numerator, when r approaches infinity, this part will approach 0. So that is the reason we must require, not must require, we can apply the similar strategy when we see this big class of integrations. It's not just for z squared over 1 plus z to 4 or 1 over 1 plus z squared. Whenever you have the difference of degrees is greater than or equal to 2, you can always apply it. And then the difficult part is to find the residue. Okay? So you just need to apply the all the algebraic trick to find the residue, and you will get it. All right. So in the exercise part on page 121, the exercise 1 part A is like this. So you're going to verify it. So you're going to compute what this is. You check here. You see the difference of degrees is also equal to 2. the minimum requirement. And 2a, the integral from 0 to infinity, that's a slightly different. X squared plus a squared, and then squared dx already done, is equal to pi over 4a cubed. Is that cubed or not? It's 4a cubed. Here a is positive. And this one is different, slightly different, because here we use a positive infinity to negative infinity. We get a semicircle, but this is from 0 to infinity. All right, so you figure out how do you solve this. It's not difficult, but figure out how do you solve it. All right. Okay. And 2f is what we just discussed. Integral. Okay. Yeah. 2f is a 1 over 1 plus x squared, but integral is from 0 to integral from 0 to infinity. It's a pi over 2, and you think about it, why it's a pi over 2. Our answer is pi. Check the upper and the lower limits. Okay, so these two examples actually represent a large class of a computation, a very large class of a computation. Okay, so now let's move to another type of computations. There's many fixed types of a computation in this part. All right. Okay, example 2.7. We're going to compute the integral from 0 to infinity sine x over x and times dx. It is equal to pi over 2. It's not like the polynomial case. When we think about the sine function in the complex analysis, we possibly will study the exponential function first. All right, we will study the exponential function. Remember that the Euler identity. In the complex analysis, we also have this. And from this we can get the relation between sine z and eiz. So in this example, we will consider the function f of z is equal to eiz over z. Over z it comes from over x, and eiz because sine z is related to eiz. Okay, consider this function. The f of z has a simple pole, just one pole. At what? At z equal to 0, just denominator equal to 0, right? Okay, so it has one simple pole. Now let's check. We are going to do the following thing. In the previous two examples, we will have some path enclosing the pole, but here we're trying to create a path avoiding the pole. Pole is here. This is 0. So we're going to do a large semicircle, a small semicircle. We'll make the larger semicircle larger and larger. We're going to make the small semicircle smaller and smaller. But this whole path does not enclose any pole. Okay? So let little r less than capital R, they are both greater than 0. And let gamma be the closed curve that is depicted in the graph. What is a gamma? Gamma means you start from little r along the x-axis, you go to the capital R, and along this upper semicircle back to negative capital R, and from negative capital R along the x-axis to the negative r, and for the r along the smaller upper semicircle from negative r to capital R, so to positive r, negative r to positive r. So you see here, you see, this is the gamma. In this gamma, you see, remember that there's only one simple pole. It's here. It's outside this path. So by Cauchy's theorem, what do we have? We have the integral of f along gamma is equal to 0. Well, nothing inside, nothing, no bad point inside, so it's 0. Well, this curve gamma, this closed path gamma is so complex. It has actually 4 parts: negative part, small upper semicircle, positive part, and large semicircle. So we will have negative part from negative capital R to negative R. This is a smaller semicircle. Oh, sorry, the negative one. It's a E I x over x dx. Right, here's a function, and it's a real axis, a real variable, so it's x from negative capital R to negative small r, plus gamma little r. Let's call this gamma little r. This gamma capital R, gamma little r, and eiz over z dz, and plus from little r to capital R, eix over x dx, and plus integral gamma along gamma capital R, eiz over z dz. All right. Okay, so with a simple modification, you will see that. Let's check sine x. Sin x, what is sin x? Sin x is eix minus e negative ix over 2i, right? Eix minus eix minus e negative ix over 2i. That's from this property, the Euler's identity. So negative capital R to negative R eix dx over x dx. Let's change. X is negative u, so it is equal to from R to R, e negative iu, negative u, negative du. Okay, so negative sign cancelled. You get negative little r to capital R, e negative iu over u du. All right, so this first term and third term, they add them together. So from R to capital R, e ix over x minus e negative ix over x dx. These two terms is exactly this, and this is, what is this? This is almost sine x, right? It is actually, the numerator is almost sine x. It's actually the integral from R to capital R, 2i sine x of x dx. Right? So first, these two terms will almost give you sine x over x, just with a coefficient of 2i. All right. Okay, now let's these two parts. Now let's study other parts. Let's talk about this gamma capital R. Gamma capital R is integral EIZ over Z dz. What is a Z? Z is capital R EIT. Capital R EIT. dz is R EIT times I dt. So dz over Z, R EIT times I dt over R EIT. Cancel this, you will get I dt. dz over Z is just I dt. So it is equal to integral from 0 to pi E I R E I T and times I and dt. Okay, times I dt. Okay, now let's put Ups value. Let's try to put Ups values. We want to estimate it. We estimate it. Let's check. I is a has a modulus of 1, so you don't have I. EIT is cosine t plus I sine t. REIT will be R cosine t plus I R sine t. And times IREIT is IR cosine of t minus R sine of t. I squared is negative. Okay, I squared is negative. And when you apply the exponential e to IREIT, you will have the real part and this argument part, not the real part, the radius part and the argument part. So let's put this modulus into this integral. And this modulus is exactly this term, all right? It is equal to the integral from 0 to pi e to negative R sine t dt. This is the argument part, so the modulus is 1. Here is the modulus. So this is the integral. Okay, so we get the integral of a function along the gamma capital R is equal to the R is bounded by the integral from 0 to pi e to negative R sine t dt. Now let's check. For gamma sufficiently small, gamma greater than 0, sufficiently small, then there is a largest possible value let me finish this and we explain of exponential of negative R sine t with t between delta and pi minus delta. Okay, so t is between 0 and pi, so sine t is a positive. Exponential of negative R sine t. All right, so let's check. This is a graph of a sine t. So if you have delta small, then delta is here, then pi minus delta is here. This is delta. This is a pi minus delta. Okay, So when you remove a little bit of 0, we don't want a 0, sine pi at 0, so we want to exclude the 0. When we remove this 0, this 0 point, when I talk about the sine t, we remove those 0 point, then you have the minimum, the smallest value. The smallest value about the sine t, this is smallest value. And times r is the smallest value, but with negative sign, it's the largest value, right? So sine t, r sine t has the smallest value on this domain delta pi minus delta. But exponential of a negative r sine t will have the largest value because it's a decreasing function, largest value on this interval, right? It will have largest value on this interval. Okay, so we'll exclude a tiny head and the tail, we can get the smallest value. Now let's check. Be careful, this smallest value is not fixed. It depends on this r. Now let's check this integral gamma eiz over z dz is going to be less than or equal to here. I'm going to integrate from 0 to delta and eiz over z. Let's put the upper value. Put the upper value, I will automatically put the upper value into it. I put less than or equal to, and plus integral from pi minus delta to pi, upper value eiz over z dz. I do not directly integrate from 0 to pi. I cut the tail, cut the head, cut the tail, and then plus integral from delta to pi minus delta eiz over z dz. All right. So we already noticed that this one is less than e negative r sine t dt, right? This one is less than it. Here it's always correct. It doesn't matter what angle you choose. This part is the same thing. E negative r sine t dt. And this part we also have this. Okay, but we're going to use a different strategy. This strategy, this one, it's a r sine t is a positive, but the negative it will be negative. Negative, so it's less than 0. Less than or equal to 0. Exponential is an increasing function, so it's less than e to 0 is less than 1. So this term is less than 1. So integrate from 0 to delta 1 dt. Here's a similar thing. Integral from pi minus delta to pi 1 dt. And this part is not, we don't use 1. We have a maximum largest possible value. What is the largest possible value? When t is equal to delta. So it's e negative r sine delta dt. All right, so for different interval, we use different estimation. Here's the delta is fixed when you have this delta fixed. Okay, it's complex, let's make it slow. Okay, now you integrate 1 along the domain. That's just a delta. Here is also the delta, the distance of the domain. And this part is going to be plus e negative r sine delta times the length. The length is from delta to pi minus delta, but we don't use this precisely is a pi minus 2 delta, but we drop this 2 delta, we just use pi. It's enough. Okay, so that's how in the textbook you just see that. You see the 2 delta plus pi e to negative r sine delta. All right. So here, why do we bother to use this delta trick to get such a computation? It is because if you do not use delta trick, negative r sine t will have the maximum value 1. But whenever you have a 1 does not involve r, then your result is just constant pi. Because you see here, it's like this, then the maximum value is a 1. You amplify you amplify it by 1, then the integral is just pi. It's a constant number. It does not depend on r, so it will not converge to 0. All right. So when you insert this delta in those head and tail part, it is dominated by the length of the domains. So the length will be small, so the integral will be small. In the middle part, it's dominated by the integrand, the function. Function is small. The domain is bounded, so the integral is also small. All right. So that's the trick and the reason we apply such so crazy trick. All right. So this delta can be between 0 and pi over 2. It's not just a fixed delta. It's whenever you have delta and pi minus delta not meet. So whenever you have a delta strictly less than pi minus delta, you can always go through those processes. So you just need delta less than pi over 2, greater than 0. That's enough. All those deltas will give you such estimation. Okay, so delta is more or less random. So given epsilon greater than 0, then there is a delta less than epsilon over 3. And once you have delta fixed, this place, delta is fixed, sine delta is fixed. Sine delta is fixed, then there is an R0 greater than 0 such that the exponential negative r sine delta is going to be less than epsilon over 3 pi. This is fixed positive number. Fixed positive number. You just make this r extremely large, so it will make this extremely negative. Exponential to 0 is going to be exponential will converge to 0 when it approaches negative infinity. So when r becomes extremely large, then you will have e to negative r sine delta close to 0. So that's why it's less than epsilon over 3 pi for r greater than r0. So we get this one, ops value less than epsilon. It means r approaches infinity, that limit is 0. Okay, it will disappear. It will disappear. This proof is a little bit tricky. If you don't quite get it, you need to go over it 1 or 2 times and check if you understand the whole steps. All right. So next, we're going to study the smaller semicircle, the other semicircle. Okay. So the other semicircle, let's check. They use another little trick. We know what is the Taylor expansion e to iz. E to z is around 0. z to n factorial n is from 0 to infinity. So the first term is 1, and then you have z, and you have z squared over 2 factorial and stuff. So you subtract e to I z. Well, you put I there, you still have a 1 as a leading term. And then subtract 1, you have I z over z. It's possible. So this one has a removable singularity at z equal to 0. All right. If it has a removable singularity, it is bounded. So there is a constant m such that the e to I z minus 1 over z is going to be less than or equal to m for all modulus of z less than or equal to 1. Over the compact set, this function will be bounded. Right. So we get what? We get the integral along little semicircle e I z minus 1 over z dz. This modulus is less than or equal to integral along gamma r e I z minus 1 over z dz, less than or equal to this integrand maximum modulus is is m. Then along upper semicircle is a pi little r. Pi little r. This is the length of the path. All right. So modulus is less than m. M is fixed in this open disk, closed disk. Pi is fixed, but r can change. R can change. R will shrink to 0. So the limit r approaches 0. The integral along gamma little r e to I z minus 1 over z dz will be 0 because it's dominated by this. So what we get this we want to break it. In order to break it, remember that the integral 1 over z dz along gamma little r, it is negative pi I. It's negative pi. Why it's negative? Because this time it's a clockwise orientation. Check here. This gamma little r is clockwise orientation. Gamma capital R is counterclockwise. This is a positive orientation. This is negative orientation. So that's why it's a negative pi I. It's just pi I because you have an upper semicircle. You do not have a lower semicircle, right? So this one always exists for whatever r. So you can get the integral along gamma little r e I z over z dz is equal to the integral r approaches 0. Limit r approaches 0. Integral along gamma r 1 over z dz. Right? So this is negative pi. This one is a constant, so you just get a negative pi. Okay, so what do we have? We have many stuffs. Remember, we have this. We have this one. 0. Little r approaches 0. Capital R approaches infinity. And the first and third term, add them together, it is this, right? These two add them together is 2i r to r sine x over x dx. And this term give you negative pi I. This term give you 0. Right? When you take the limit, r approaches infinity, little r approaches 0, capital R approaches infinity. The first and third term give you 2i integral little r capital R sine x over x dx. And the second term give you negative pi. We just compute negative pi because it only contains little r, not contain capital R. And the term, the fourth term give you 0. We compute it, the limit is 0. Alright, so you will have this integral is equal to pi half. And that's it. That is the answer. Okay, so this is a very long and complex example. Almost all the steps contain tricks. So you must examine this several times and try to reproduce it without consulting the textbook. See if you can go through the steps. If you can do that 1 or 2 times, you will consider it, you understand it. Okay, so we finish this video. We will continue other examples in the next video.